Energy resources, a scientific and technological problem of the 21st century. In the previous lecture, we discussed about conventional oil and gas production and consumption. We will now describe the new frontiers of conventional oil and unconventional oil and gas resources. Let us now review the opportunities of increasing conventional oil. The current projections are that we will need to produce about 130 million barrels of oil per day by 2030 to keep up with world demand. Experts in population growth and in economic cycles believe that this figure is conservative. The present world oil production is about 90 million barrels per day. Where will the extra 40 million barrels per day come from in 2030 and beyond? A quick run-through of the 800 or so fields which provide the bulk of our current oil consumption shows that the production rates of most of these fields have passed their peak. So the pressing challenge is to halt the decline in oil production and at best achieve an increase in oil production of, say, 100 million barrels per day. In light of these numbers, the whole debate about conventional versus unconventional oils and renewable versus non-renewable sources of energy seems misplaced if we can reduce or capture the carbon emission of fossil fluids. In any case, at this rate, it looks like we will need all these sources of energy, but will still fall short of keeping up with world energy demand for some years. Areas with the potential for new sources of oil are in the so-called ultra-deep waters. These are water depths greater than 1,500 meters of the Gulf of Mexico, the Gulf of Guinea, and the coast of Brazil. Offshore oil and gas exploration and production, or E&P, in water depths less than 200 meters are characterized as shallow water E&P. Offshore oil and gas exploration and production in water depths greater than 200 meters but less than 1,500 meters are characterized as deep water E&P. When the water depth is equal to or greater than 1,500 meters, that is, about 40 kilometers or more from the coast, the E&P is characterized as ultra-deep water. Again, areas with a potential for new sources of oil are in the so-called ultra-deep waters. These are water depths that are greater than 1,500 meters of the Gulf of Mexico, the Gulf of Guinea, and the coast of Brazil. The recoverable reserves in the ultra-deep waters of the Gulf of Mexico are estimated to about 25 billion barrels. This picture of the Gulf of Mexico includes the famous coastal towns of Houston and New Orleans. The red circles indicate new oil fields in 2015. Notice how far these fields are from the coast. The Carioca Sugarloaf field is an ultra-deep water oil field in the Atlantic Ocean off the coast of Sao Paulo, Brazil. The field is part of an important petroleum basin known as the Santos Basin. Two other large ultra-deep water oil fields in this basin are the Tupi and Jupiter oil fields. Ultimate recoverable reserves of the ultra-deep waters of Santos Basin are estimated to be about 40 billion barrels. The concept of matching geology between the two continents is very important for oil and gas industry. actually mining industry in general. There are large reserves of oil in ultra-deep waters of the coast of Brazil. Similar large reserves are expected in ultra-deep waters of West Africa. Current estimations are that there are more than 40 billion barrels of recoverable oil equivalent in the ultra-deep waters off the coast of Brazil. The geology of the Gulf of Guinea is very similar to that off the coast of Brazil. So we can expect that about 50 billion barrels of recoverable oil equivalent or more remains to be discovered in the ultra-deep waters off the Gulf of Guinea. The reservoirs in ultra-deep waters have low permeability and high viscosity, and are located below salt bodies. In other words, ultra-deep water reservoirs are very different from reservoirs currently in production. We have to drill through the salts to 5,000 meters or more below the seafloor. The ultra-deep water drilling rigs in 2015 cost more than $2 million per day. This is a significant cost that considerably reduces the number of industry players in ultra-deep waters to just a handful. Let me repeat that the ultra-deep water drilling rigs in 2015 cost more than $2 million per day, which is a significant cost that considerably reduces the number of industry players in ultra-deep waters to just a handful. Furthermore, environmental issues such as weather patterns, hurricane severity, near sea bottom currents, and more, also safety challenges, are equally important. More specifically, the exploration and production challenges in ultra-deep waters differ from those in shallow waters, and even in deep waters, for the following reasons. 1. Major environmental and safety issues. 2. Extreme temperatures, 350 degrees Fahrenheit or more, and extreme pressure, about 30,000 psi or more, at the seafloor and below. 3. The thick salt layers overlying these reservoirs. 4. The low permeability and high viscosity of oil in these reservoirs. The permeability is so low in some cases that fracking is now extending to offshore. In a large number of ultra-deep water cases, the recovery factor is less than 20%. In other words, more than 80% of oil is dispersed in the ground when production is abandoned. The low recovery factor is the result of the low permeability of the reservoirs and the high oil viscosity. While 20% of a billion-barrel reservoir is a significant output for most oil companies, it is probably a high price for the environmental damage associated with oil production architecture. Let's use the analogies of trees producing fruits to try to understand ultra-deep waters E&P. Starting with trees and fruits, let's think about a fruit-producing tree. At some point in time, the tree will naturally produce fruits that can then be picked for consumption. With ultra-deep waters, through billions of years of biogenic and thermogenic processes, the Earth has naturally produced large accumulations of oil, such as Gawar, Dowing, Somot-Lor, Prudhoe Bay, and Cantarell. These are supergiant and giant oil fields. Going back to trees and fruits. Through the fruit picking process, the fall of fruits from trees and/or the spoiling process, all the mature fruits will disappear. We will have to wait for some time for new fruits to mature. That is why some fruits are seasonal. Going back to ultra-deep waters, through exploration, all the supergiant and giant fields have been discovered, and no new ones will be found for a while, irrespective of technological advances in oil exploration. We will have to wait a couple of million years for new giant fields. With trees and fruit, one can consider a premature picking of immature fruits. However, traditional ways of consuming fruits and/or processing them for consumption do not work. Even traditional methods of picking these fruits may work for a premature picking of immature fruits. With ultra-deep waters, one can consider tapping of some oils at an early stage of formation. Oil at this early stage tends to be located 5 kilometers below the sea floor in ultra-deep waters. The oils still have a significant possibility of upward motion and even lateral motion. The reservoirs are very heterogeneous because we are still in the earlier stage of their maturation. With trees and fruits, we have to design new ways of picking immature fruits and new processes for turning them into consumable products. Significant parts of these fruits must be discarded. Another approach is to let the tree naturally produce its fruit at its own time. Some early fruits will never mature, but a significant number of early fruits do mature naturally and are good for consumption. With ultra-deep waters, traditional exploration and even production do not work. New developments in E&P and even in downstream are needed. The recovery factor of these oils are very small compared to that of conventional oils. Another approach is to let ultra-deep water reservoirs mature. In other words, one can consider tapping some oils at an early stage of formation. Oil at this stage tends to be located 6 kilometers or more below the seafloor in ultra-deep waters. The oils still have a significant possibility of upward motion and even lateral motion. The reservoirs are very heterogeneous because we are still in the earliest stage of their maturation. Another important challenge in ultra-deep waters is that the classical equations of state between pressure, volume, and temperature, and the associated transport properties do not hold for pressures higher than 20,000 psi and heavy viscous oils, which is the case in ultra-deep waters. The scientific and technological challenges associated with the exploration and production of these resources are enormous. Furthermore, the environmental issues are significant. In summary, it is a huge risk to hope that ultra-deep water oil production can significantly increase global oil output in the near future. This picture is related to Macondo oil field in the ultra-deep water Gulf of Mexico on April 20th, 2010. The Macondo oil field is operated by BP. Following the explosion and sinking of the oil rig, a seafloor oil gusher flowed for 87 days until it was capped on July 15, 2010. 11 people went missing and were never found, and it is considered the largest accidental marine oil spill in the history of the petroleum industry. The U.S. government estimated the total discharge at 4.9 million barrels. Another new frontier is the Arctic Ocean. No business may be called efficient if it threatens the environment in which we live and work. The potential damage to the environment includes health and safety hazards, endangered species, habitats, and vegetation are affected. Also temporary closings of access roads and more. There is no place in the world where these potential hazards are more acute than the territories around the Arctic Ocean. Yet these territories may contain much of the world's remaining conventional oil and gas. Because the Arctic has a forbidding climate and is remote from the world's markets, it has remained among the least affected by human industry. Nevertheless, oil exploration and production have been underway for many years in parts of Alaska, Canada, and Siberia. Arctic territories are covered by a layer of permanently frozen subsoil permafrost, up to 1,500 meters deep and overlain by a variable layer of soil that thaws in the summer. The vegetation is very sensitive to change and is extremely slow to recover from damage because of the low temperatures. To avoid unnecessary clearing of vegetation, oil explorations are essentially conducted in winter, when there is sufficient snow to cover the underlying vegetation. In Alaska, permits to conduct operations are not issued until there are at least 15 centimeters of snow. We expect that the advances in ultra-deep water exploration and production will facilitate advances in other frontiers of exploration and production, such as the Arctic basins. Lessons learned in drilling below 5,000 meters depth and in regard to environmental issues associated with ultra-deep waters will be useful. Note that USGS estimates recoverable reserves to be 90 billion barrels of recoverable oil for the entire offshore Arctic. In the portion of the Arctic OCS that the U.S. controls, the Chukchi and Beaufort Seas of the North Slope of Alaska, the estimate is 9 billion barrels of recoverable oil. The other challenges of Arctic exploration and production include moving sea ice, ultra-remoteness, oil spill risk on broken ice, and more. It is safe to assume that many of the wells drilled in the Arctic will be as deep as in ultra-deep waters, surpassing 5,000 meters in total depth. So, Arctic and ultra-deep water oils, for which ultimate recoverable reserves are still unknown, are the new frontiers of E&P. Let us now review the opportunities of increasing oil and gas through the use of unconventional resources. With the dwindling of conventional oil resources, the E&P industry is turning more and more to unconventional oil resources, namely shale gas, heavy oil, tar sand, also known as oil sand. These oil resources are characterized as unconventional because they do not flow like conventional oils do. In some cases, they do not flow at all. Moreover, methods of exploration and production, even of the refining of these oils, are different from those of conventional oils. Notice how the unconventional oil and gas has changed the U.S. production curve. Natural gas can also exist in shale deposits, which formed about 350 million years ago. Shale, which consists mainly of consolidated clay-sized particles, is the Earth's most common sedimentary rock. Shale has very low permeability. In many oil fields, shale forms the geologic seal that retains the oil and gas within producing reservoirs, preventing petroleum migration to the surface. In a handful of basins, however, layers of shale, sometimes hundreds of meters thick and covering millions of acres, are both the source of and reservoir for natural gas. Owing to breakthroughs in technology, especially in the U.S., production from shale formations has gone from a negligible amount just a few years ago to being almost 30% of total U.S. natural gas production. Here are the major shale gas basins in the United States. There is a total resource potential of 500 to 1,000 trillion cubic feet. TCF stands for a trillion cubic feet, and BCF stands for a billion cubic feet. Large shale gas resources exist worldwide. The EIA map here illustrates this point. The shale gas resources in Europe are primarily located in the Ordovician allume shale of Scandinavia and the Permian Carboniferous shale of the Paris Basin. Actually, France, Poland, Germany, and Sweden hold the largest share of shale gas resources in Western Europe. South America also has large resources in 4 major shale gas basins: Neuquén, San Jorge, Austral Magallanes, and the Parana-Chaco complex. Notice that this map is incomplete. Significant areas of the world, including Russia, the Middle East, and Africa, are not included in the EIA study. With the first order view of the gas in place, we have used the plate tectonic theory to extrapolate the EIA map to areas not covered by this study. The extrapolation here consists of putting the shale gas resources as predicted by the EIA on the world map of 400 or so million years ago. We then consider the fact that continental margins previously shared stratigraphic units and a tectonic history before and during the continent's breakup. As a result, shale basins can be extrapolated beyond the EIA map, an approximated world map of shale gas resources. This map is an extrapolation tectonic plate theory. The production of shale gas requires drilling horizontally through the shale formation and fracking the shale to artificially induce permeability. Today, hydraulic fracturing is the preferred way of artificially making shale permeable. In its simplest form, hydraulic fracturing, or perforation, consists of pumping a very large mixture of water and sand into a well. Let's talk more about tight gas. Tight gas refers to gas that is stuck in a very tight formation underground in unusually impermeable hard rock, or in a sandstone or limestone formation that is unusually impermeable and non-porous, as shown here. In a conventional natural gas deposit, once drilled, the gas can usually be extracted quite readily and easily. A great deal more effort has to be put into extracting gas from a tight formation. Several techniques allow natural gas to be extracted, including fracturing and acidizing. Most tight gas formations are found onshore. Now let's move to gas in high pressurized zones. A significant number of formations are under unusually high pressure for their depth. These areas are formed by layers of clay that are deposited and compacted very quickly on top of more porous absorbent material, such as sand or silt. Water and natural gas that are present in this clay are squeezed out by the rapid compression of the clay, and they enter the more porous sand or silt deposits. Because of the compression of the clay, natural gas is deposited in the sand or silt under very high pressure. These zones are easily detected. However, the high pressure and the fact that these high pressurized zones are typically located at great depths, usually 3,000 to 7,500 meters below the surface of the Earth, make the extraction of natural gas in these zones quite difficult. Now let's talk more about coal bed methane. Coal, another fossil fuel, is formed underground under similar geologic conditions as natural gas and oil. The coal deposits are commonly found as seams that run underground and are mined by digging into the seams and removing the coal. Many coal seams also contain natural gas, either within the seams themselves or the surrounding rocks. Now let's talk about gas hydrates. Someday, perhaps in the 21st century, the Earth's store of hydrocarbons will no longer supply adequate energy to its growing economies and population. By then, the unfamiliar but kindred hydrocarbons called gas hydrates may be ready to complement hydrocarbons as a significant source of energy. Gas hydrates are a special combination of two common substances, water and natural gas, or methane. If these substances meet under conditions in which the pressure is high and the temperature is low, they join to form a solid ice-like substance. Gas hydrates have been found at the seafloor, but their usual range is 100 to 500 meters below the seafloor. Large accumulations have already been identified offshore Japan, on the eastern seaboard of the United States, on the Cascade continental margin off Vancouver, in Canada, and offshore New Zealand. Vast volumes of sediments on the ocean bottom and in the polar regions are conducive to gas hydrate formation. Most gas hydrates seem to be confined to the edges of continents, where nutrient-rich waters unload organic detritus for bacteria to convert to methane. Recovery of gas hydrates is not currently feasible. Let's talk about heavy oil. In the oil and gas industry, fluid densities are commonly described on an American Petroleum Institute gravity scale, defined as follows. Although API gravity has no units, it is generally referred to in degrees. The API gravity of water is 10 degrees. Oil samples described as high gravity are lightweight, and heavy oils have a low API. Oil is considered, if its API gravity is greater than 31 degrees, medium. If its API gravity is between 22 and 31 degrees, and heavy, if its API gravity is less than 22 degrees. Heavy crude oil does not flow easily because it is highly viscous. The largest reserves of heavy oil in the world are located north of the Orinoco River in Venezuela. This is nearly 90% of the world's heavy and extra heavy oil. Most of the remaining reserves are located in Canada and Russia. Heavy oil are very difficult to produce and cannot be refined in traditional refineries. Let's now turn to tar sands. Heavy crude oil is closely related to tar sands, the main difference being that tar sands generally do not flow. Tar sands, also known as oil sands, are sand deposits with 1 to 20% of bitumen. Bitumen is an extra heavy oil with an API gravity of less than 10 degrees. It is too viscous to be pumped. It won't flow at room temperature, and it must be heated. Canada is the leading producer of these unconventional oils. In Canada, open-pit mining of shallow oil sands provide approximately 50% of the nation's heavy oil. In situ production of heavy oil with sand and thermal production using injected steam provides the remainder of Canada's production. Steam-assisted gravity drainage, or SAGD, this production is rapidly growing. SAGD thermal recovery combines horizontal drilling with thermal steam injection. A pair of wells is drilled into the ground about 5 meters apart, and steam is injected into the reservoir through the top well. The steam softens the tar-like bitumen and enables it to flow out of the reservoir and into the lower well. From there, it is pumped to the surface. Now let's talk about oil shale. Oil shale, generally known as the rock that burns, is another potentially important resource. Large accumulations are found in the western U.S., Canada, and Australia. Oil shale accumulates as clay-rich sediment that has trapped abundant organic material with a small pore space. Oil shale recovery is also based on mining. Oil shale is far more energy intensive to produce. It is not an easy substitute for natural gas and light oil. Shale contains abundant keratin. Let's conclude with a very brief review of the oil industry. Oil companies, including public and independent oil companies, acquire exploration leases or acreage from governments or landlords and explore for oil and gas in many parts of the world. They usually do not have their own seismic data acquisition crews or drilling outfits. They use the specialized services of service companies to meet their operational objectives. A service company provides technical and expert specialized services to oil companies. A service company, such as Schlumberger, provides seismic data acquisition, seismic data processing and interpretation, wireline data acquisition, drilling and measurement, petrophysical data processing, interpretation services, and more. Actually, the small oil companies tend to outsource almost all of their E&P business and focus primarily on the acquisition of leases and on the late stages of exploration. Thank you for listening to this iMode Education lecture. Remember, there is a large selection of iMode Education lectures which can further enhance your knowledge of energy.